What I plan to do today is to continue talking about the sampling distribution of sample means. And yesterday we talked about the center and spread for the sampling distribution of sample means. The mean of X bar is just the mean of the population. And the standard deviation of X bar is the standard deviation of the population divided by the square root of n, provided the 10% condition is met. Okay. So we've got the mean, we've got the standard deviation, so that's the center and the spread. Now we want to talk about the shape. So the shape is pretty straightforward as long as the 10% condition is met, and if the population is normally distributed. If it's normally distributed with a mean of mu and a standard deviation of sigma, then the sampling distribution will be normally distributed with a mean of mu and a standard deviation of sigma over the square root of n. So that's a whole lot easier than dealing with the sample proportion. In fact, it's almost so easy that it doesn't seem right. It seems like, wow, that's really too easy. But that's the way it works out. If we're taking samples from a population that is normally distributed, then our sampling distribution will be normally distributed, as long as the 10% condition is met. If this condition is not met, then all bets are off and we have to go some other route. But if this condition is met, then we're in good shape. We know that the sampling distribution will be centered on the population mean, and we'll have a standard deviation, which is just divided by the square root of n compared to the population standard deviation. Okay. So that's pretty straightforward. And let me see, what do I want to do next? Okay, so what I want to do next is I'm going to give you an example straight out of your textbook, and I'll walk you through it. It's on page 447. So I'll give you a minute to turn there. All the steps are kind of worked out for you, so I'll really just walk you through that. We'll talk about it, and you can ask questions. I do have my solution here step by step, but it's really not that much different than the solution that's in the textbook. So let me just kind of read through it for those of you who don't have your book in front of you. The height of young women follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5. Now, we're not given a lot of information here, but I'm assuming this is the population of young women in the United States. I would think it would give us something else if it were an international population. But anyway, so what we want to do is we want to find the probability that a randomly selected young woman is taller than 66.5. So if the mean is 64.5, we want to randomly select one person out of that population and figure out what's the probability that her height is greater than 66.5. Well, this should be pretty easy for us now. That is what we've been doing all year long, finding the probability of a particular value on the normal curve. We'll calculate a z-score, look that up in table A, and compare that with, and then read the probability off of there. Part B is the new part. That's what we're doing now. Find the probability that the mean height of a simple random sample of 10 young women is greater than 66.5 inches. Okay, so the scenario here is that we're not just selecting one person at random. Now we're selecting 10 people at random using a simple random sample. And so that's going to get us into calculating the mean and the standard deviation of the sampling distribution. But so the first part, part A, that's really straightforward. We're just going to take our value X as 66.5, use that to calculate a z-score, 66.5 divided by 64.5, all that divided by 2.5 gives us a z-score of 0.8. And then from table A, the probability that z is greater than 0.8 is the same thing as the probability that it's 1 minus z of 0.8. So that's 1 minus 0.788. That gives us a probability about 21%. Okay, so if we were to take this population of young women, randomly select one person out of that group, there's about a 21% chance that she has a height taller than 66.5 inches. So that's 5 feet 6 inches. Let's see, how many ladies on the screen do I have taller than 5 inches? Bethany, I bet you are. Riley, are you taller than 66? 66?
I'm 5'6".
So I've got five women here, and 1 out of 5 of you is taller than 66.5 inches. So how about that? Well, I don't know. Brianna, are you taller than 66.5? I don't know. But anyway.
Yeah, I'm like 5'8".
Yeah. Okay. All right. Well, so 2 out of 5. All right. Well, but you get the idea that you can kind of get a feel for the probability of one person in that group being taller than 66.5 is about 20%. Okay. So now let's take a look at part B, the simple random sample of 10 women. And so first of all, we have to confirm that the 10% condition is met. And so in other words, with a simple random sample of 10, then our population needs to be greater than 100 in order for that to be satisfied. And with no information given, we're going to assume that it's a really broad population. So oftentimes what you see me do here is that I would write something like little n is less than or equal to 1/10 of some big number. Okay, and so that means the 10% condition is met, and we can go forward knowing that that sampling distribution now is also normally distributed with the mean of the same as the population mean, but we're going to have to calculate the standard deviation. So all we do is we take the population standard deviation, 2.5 divided by the square root of 10, number a little bit larger than 3. And so when we do that division, we get a standard deviation of 0.79. And I don't want this to be lost on you. So flip the page to page 448, and let's look at that diagram right there. And I think I'm going to try to share the screen here and show you that picture on the screen right here. Can y'all see that picture now? It should be the same thing you see on page 448.
Yes.
Okay,
Yep.
so the distribution on the bottom is the population distribution. Okay, so that is the distribution from which we drew the sample. Here's the goalpost, 66.5 inches that we're looking for. The area that we're looking for, I wonder, let's see. Can I mark on this? Let's see. Let's try it. Yeah, we'll just try a pen. Look at there. Okay, the area we're looking for is this area right here. To the right of the goalpost. And so that area is quite a bit larger than the little bitty tail that you see from the sampling distribution. Notice that the sampling distribution is centered on the mean. It has the same value as the mean. It's centered on the mean, but look how narrow it is compared to the population distribution. And so the area we're looking for in part B is this tiny little area. Let me pick a different color. It's this tiny little area right here. Okay, just in that little corner. And so the probability that we're going to get an average of 10 is really small compared to the average, the probability of just getting 1. So that's the value we're trying to calculate, is this little tail right here. So what we have to do is we'll go back. You can take a look back at the textbook now. We're going to calculate a new standard deviation by dividing by square root of 10. That gives us 0.79. When we calculate the z-score now, the z-score is 2.53, which means we're over 2.5 standard deviations away from the mean of the sampling distribution. So that's a pretty small number. You see a z-score of 2.5 and you know that's going to be a small number. And sure enough, when we calculate that value, it is 0.0057, or about 0.6% chance that the average of the 10 would be greater than 66.5. Okay, so that's pretty unlikely that we're gonna get that value, or that we're gonna get a sample of 10 in that group. Okay, so that's what we're after now, is the ability to make a distinction between the population distribution and the sampling distribution. And we know that the sampling distribution, as long as the population is normally distributed, we know this shape is going to be normally distributed. And we know it's going to be centered on the population mean. It's just that the variability of this distribution is a lot less than the variability of the population. Okay, so any questions? All right. So that's really the trick. We're just going to be comparing values from a population versus values from the sampling distribution. And so now I want to put up another question, almost identical in nature with a little bit different context. Right here, the Peanutty Peanut Company, they sell dry roasted peanuts in jars, which makes me really hungry right now. The distribution of the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15. Okay, so part A says, without doing any calculations, which is more likely? Randomly selecting a single jar and finding the contents to be less than 16, or randomly selecting 10 jars and finding the average of the contents to weigh less than 16? Okay, so if somebody want to take a chance, tell me what you think.
I'll say the average one.
The average one. Yeah. Yeah. Now tell me why.
Because there's more jars for you to look at. I guess it increases the probability or something like that.
Or something like that. Yeah. Something like that. Okay, so in light of the diagram that we just looked at, let me draw another one here. Okay, so I've got the population distribution is normally distributed with a mean of 16.1 and a standard deviation of 0.15. So that's what you see here. Normally distributed, I hope you can see that without too much reflection. Normally distributed.
Are you drawing something?
Yeah, can you see that? Oh, I need to stop sharing my screen, don't I?
Yeah.
What a dumb. I'm so sorry. Y'all deserve so much better. Now, how about that? Does that make more sense? Can you see that? Okay, so the population distribution, 116.1 and a standard deviation of 0.5. So it's kind of flat. Now, when I draw in the sampling distribution, first of all, we have to ask our question, is the 10% condition met? So tell me, do we think our sample of 10 jars is, wait a minute. Let me go back and look at the first part. Okay, so we want to find the probability that a single jar is less than 16 ounces. So that's this area. That's that area right there, right? Less than 16 ounces, a single jar. We want to compare that to the probability of a sample of 10 jars. So before we do that, we have to ask the question, is the 10% condition met? So tell me, is the 10% condition met here? How many jars are in our population? How many jars in the population?
I don't remember. We can't see it anymore.
It's what?
None of us remember.
We can't see it.
You can't see what anymore? You can't see this?
No, the problem.
That just tells me.
Oh my goodness. Okay. This is so complicated.
I think you can just
Here
leave
we
it.
go. I'll flash it back up there.
You
There.
should be able to just leave it because I think we can click back and forth on what we see. Both of your screens.
Can we?
Yeah.
What?
You can click on.
Leave it like this.
We can click on which screen you have. So like I can click on you and I can click on your presentation screen.
Oh, this is true. And just with the little pin thing?
Yeah.
Oh, okay. Well, isn't that cool? Learn something new every day. Okay, so how big is the population of the jars of dry roasted peanuts?
We don't know.
We don't know precisely, but we know it is big. We know it's big. Okay.
Yeah.
They're in the job of making dry roasted peanuts, and so with a simple random sample of 10, population only has to be larger than 100. So do we think that they've probably made more than 100 jars of dry roasted peanuts?
Yes.
And we're going to say, yeah, that's a pretty good assumption. With a name like Peanutty Peanut Company, they're pretty big. So we're going to make the assumption that the population is large enough that a sample of 10 meets that 10% condition. Okay, so now that we've made that assumption, we want to draw the sampling distribution. So the sampling distribution is going to look, ooh, that's terrible. Let's see that one. That's a little more better. Okay, I'm putting this in front of the camera now. Can you all click back and forth to the camera?
Yep.
You will? Okay, so the sampling distribution is the purple curve. It's skinnier and taller. By the way, just for bonus points here, why is it always going to be taller?
Less variability.
Well, less variability makes it skinnier, but what makes
More bias.
more what?
Bias. Less bias.
It's
I don't
well, if it's got the same mean as the population, it's got zero bias. It is a perfect estimator of the population.
Okay, scratch that.
Because your
Go
n
back
is
to our
changing.
discussion. What's the area? What's the total area under the big curve to begin with?
One.
Oh, because no, never mind.
There's
Wait,
a lot
say
more
that again?
possible samples than
Yeah,
the population.
What's the area under the population curve to begin with?
1.
1. What's the area under the sampling distribution curve?
No, 1.
It's 1 also, right? It's
Mhm.
of a density curve. The area under the curve is always equal to 1. So since the area stays the same, if I squish the ends of it together, then it's like squeezing a balloon. The air has to go somewhere, and it goes up and makes the distribution taller and skinnier, which makes sense with what we've been talking about, because what we're saying, somebody mentioned this idea of bias. What we said is that this is a really good estimator. The mean of the sample is the same as the mean of the population. So it's a perfect estimator. And so what that means is the more samples I take, the more likely it's going to be really, really close to the mean. And we can see that now. We can see that now as I color in the little piece of the curve that is to the left of the 16 ounces is so much smaller than the piece of the curve to the left of the 16 ounces for the population distribution. So, so we would expect, because of that lower variability, that we're more likely to find one jar less than 16 ounces than we are the average of the jars. Okay, and the whole reason for that is because this sample mean is equal to the population mean. That makes it a perfect estimator. And so we're really, really happy about that. And the reason that it's such a good estimator is that our population is normally distributed to begin with. Okay, with a sample size of 10, if the population is normally distributed, we're in good shape. Now, in just a second, when we talk about the central limit theorem, a sample size of 10 is not going to be good enough. We'll have to do better than that. But in this case, with a population that's normal to begin with, sample size of 10 is probably good enough. Okay.
So, like, there's no math when you try to do that? You just look at the graph?
Well, part B, if you'll switch back to the problem statement, part B says find the probability of each event described. Okay. So yeah, there is math. What I'm trying to do with part A here is to get you to grasp conceptually what you see in this diagram. Is I'm comparing the tiny little purple portion with the much bigger shaded portion. Shaded portion represents pulling one jar off the line and getting getting a weight less than 16 ounces. The purple portion is the probability of pulling 10 jars off at random, weighing all 10 jars and getting an average less than 16. Looking at the area under the curve, the likelihood of getting an average of 10 less than 16 is much smaller than the likelihood of getting a single value less than 16. So conceptually, that's what's going on here. And that makes this part of statistics so valuable, is that if I take a simple random sample from a population, and I know the population is normal to begin with, and I know my sample is going to point me to the mean. Because remember, we don't always know what the mean of the population is. Think about you being a worker at the Peanut Company. They produce thousands, maybe hundreds of thousands of jars of dried peanuts a day. How are you going to know what the mean of that entire population is unless you go and weigh every single one of them? Okay, that's a really big task. So what we choose to do, take a random sample of 10, and that will point us to the mean of that sample is going to point us pretty close, pretty doggone close to the mean of the true population mean. And that's how powerful what we're doing is here. And it's used every day in real world applications. I mean, it's really, really, really powerful, a really, really common technique. Okay. So it's really easy. I won't say really easy, but it's much easier when the population is normally distributed to make these calculations. All we have to do is verify the 10% condition is met, and then we can go and make that calculation. Okay, so part B says find the probability of each event described, and so I'm just going to kind of talk you through this. I'll send you my written example of this, but it's going to follow the same steps as the example on page 448. Okay, so for the first one, taking a single sample, we're going to calculate a z-score. We're going to use let's see, we're going to use an x value of 16. The mean will be 16.1. We'll divide that by the standard deviation. We'll get a z-score of negative 0.67. You go and look that up on the table A, and the probability of a value less than negative 0.67 is 0.25. That number might ring a bell because 0.25 is, that's the 25th percentile. We've talked about that a few times. So there's a 5% chance that you can select one jar off the line and it's going to weigh less than 16 ounces. So a 25% chance. Now for the randomly selected 10 jars, the only difference in my calculation here is I'm going to have to recalculate the standard deviation. So I'm going to take that standard deviation of 0.15, divide it by the square root of 10 again, and I get a value of, well, I didn't write it down. I'll be sure and write it down for you when I send you my notes here. But 0.15 divided by the square root of 10, 0.15 divided by 3, that should be about 0.05. Yeah, it's 0.047. So when I calculate that z-score, again, I'm going to use the value that I'm interested in is 16 ounces. So 16 minus 16.1. And I'm going to divide that by 0.047. That gives me a z-score of negative 2.11. We'll call it 2.11. And the bell should be going off. I've got a z-score negative 2.1. So that's over 2 standard deviations away from the mean. That's a really small value. And when I do the calculation, that it gives me a probability of 0.0175. Okay, 0.0175. So about a 2% chance. Remember, 2% is less than 5%, so that's pretty unlikely. So obviously, it's more likely to get a single value than it is an average of 10. Okay. Okay. So just for grins, let's since I've got one of the things I can do on the screen here is I can refresh your memory on how to do those calculations using the calculator. So I'm going to put the calculator up on the screen, and we'll go through and we'll use the Normalcdf to calculate the probabilities of each of those. Okay, can you see the calculator okay? Everybody
Yep.
see the calculator? Yeah, okay, good. Okay, so to do this calculation without table A, I'm going to go to second function distribution. And I'm calculating an area. I want to know the probability to the left of a particular value. So in the first calculation, I'm going to use, for both of them, I'm going to use Normalcdf for cumulative distribution function. My lower goalpost, since I'm looking at a left tail, is a really small negative number. So negative 10,000 ought to do. My upper tail is the goalpost of 16 ounces. Whoops, not 156. 16. Okay, my mean was 16.1, and my standard deviation was 0.15. Okay, so I paste that in and I do the calculation. And sure enough, there's my 25% or 0.25. Now this value to 4 decimal places could be slightly different than what you see on table A. We said on table A that it was 0.2, yeah, 2525. Yeah, so that's pretty close to table A. No, that wasn't table A. Let me get table A. Table A,
Yeah, we said 0.25.
yeah. Well, I'm looking at, let's see, the z-score was negative 0.67. Crap. Negative 0.67. And if I'm looking at table A correctly, negative 0.67 is 0.2514. So it's pretty doggone close. Pretty doggone close, but slightly different. And that's just the round off error in that our z-score is not really negative 0.67. It's really negative 2/3. So that is rounded up a little bit. Okay. So now the tricky one is finding the probability that our sample of 10 is going to be less than 16 ounces. And this is where the Normalcdf calculation comes in really handy. because we can do all of our arithmetic here. The lower bound is still a really big or really small negative number, or really big negative number, negative 10,000. Our upper bound is still the 16 ounces. Our mean is still the mean of the population, 16.1. The standard deviation, however, is the population standard deviation, 0.15, divided by the square root of 10. So I can do this arithmetic right here, and I don't have to do it. I don't have to do it in a separate space. I can just type it in as I go. Okay, so now when I plug that in and I hit enter, there's my 0.0175 that we got before. Okay, so that's just kind of a refresher on using normal CDF function on the calculator. If you like table A, then stay with table A. If you like using the calculator, then stay with the calculator. One is not better than the other. Honestly, I'm not sure that one is really quicker than the other. So just whatever you feel more comfortable with, that's the one you should start using over and over and over again. Okay.
So you don't do anything different because you're finding a average of a sample data. You just do it the same. You just change the
The only
deviation.
difference, yeah, the only difference in this particular calculation is the standard deviation changes, where I have to divide by the square root of n. And that's what shrinks the standard deviation and makes my sampling distribution of sample means skinnier than my population mean and much taller.
I'm working on network documentation, working with Visio. There's a pretty large network diagram. Created. Spent a few days working on that, trying to get it updated with current switches and current information.
Somebody's asking a question, but I can't hear you.
Information in there. Like Brandon said, we went in on Friday.
It's probably my dad talking in the background, to be honest.
Oh. Well, say hi. Yeah, okay. Then never mind.
He said to be honest.
I'm gonna ignore his question then, and I'm gonna keep going.
Okay.
Okay, so I'm going to take the calculator down here, and I'm going to skip over. You can turn in your textbook to page. We're going to talk about. I'm going to introduce you to the central limit theorem, which, if we were in class today, I would have some really cool music playing, because this is one of those memorable days in your stats class. The first time you talk about the central limit theorem is kind of like the first time you get table A. It's really a big deal. Central limit theorem is a big deal in stats. Here we go. Limit theorem. If you turn to page 450 in your textbook. Page 450 in your textbook. Okay, so normally in class, I'm going to be writing the definition of the central limit theorem in this space right here, but I'm not going to do that now. I'm just going to show these diagrams, and these diagrams are in your text. But in the middle of page 450, in the green box, is the definition of the central limit theorem. And it says if you draw a simple random sample of size n from any population, A-N-Y, any population with a mean of mu and a finite standard deviation, the central limit theorem says that when n is large, the sampling distribution of the sampling mean is approximately. Okay, so two things that jump out right there that I want to make sure I point out. First of all, It says the sampling distribution of the sample mean. Every year I give a couple of questions on the chapter test here about the central limit theorem. And students get this confused, so I want to start from the beginning. The central limit theorem only applies to a sampling distribution of sample means. Central limit theorem does not, capital N-O-T, apply to the sampling distribution of sample proportions. Okay, we've got our own rules about sample proportions and the shape of the distribution there. Central limit theorem only applies to a distribution of sample means. Okay, so if I'm counting things, the central limit theorem does not apply. If I'm measuring things, then it might apply. And it applies when n is large. Well, how large is large? Good question. I'm glad you asked. Let's look at the diagrams you can see on the screen now, okay? So here, the diagram at the top is our population. And even Stevie Wonder could see that this population is not normally distributed. It is not symmetric. It is not single peaked. It is not bell-shaped. It is not well behaved at all. I have no idea what this population is. My guess is it's just some sort of made up graph. But if this represents my true population, a couple of things. The center of the population is going to be somewhere in the center of the graph. I'm not really sure exactly where. And we might read it, we might, in the green box there, it might tell us. I've got my wrong glasses on. I can't read the green box right now. But anyway, here's the key thing. If I take, I think it's 100 samples. If I take 100 samples of size n equals 2 from this population, and I make a histogram of the average of those two samples, that's what the histogram begins to look like. And you can see I'm beginning to fill in these gaps between the three peaks. And overall, I'm beginning to see a much more well-behaved shape here. If I increase my sample size from 2 to 5, if I only go from 2 to 5 and I take 100 samples out of this population and I calculate the mean of those 5 samples, so I add up my 5 values, divide by 5, and I plot all of those 100 values, this is what I get. And man, it's beginning to take shape. I would begin to say, hey, this is approximately symmetric. It's definitely single peaked, and it's almost bell-shaped. If I change that sample size from 5 to 10, then it even gets better off. And notice this red bar at the bottom here. This red bar represents the standard deviation. So here's the standard deviation. I think it's 1 standard deviation of the population. And then when I start sampling from the population, notice how skinny this value becomes. And then finally, I get a sample size of 25. And I add up the 25 values. I find the average, and I do that 100 times. Look at this thing. This is beautiful. This is definitely something I would describe as approximately normal. It's single peaked, it's bell shaped, and it's centered. If you could blow up the graph, you would look and see that it's centered at about the same place this one's centered. The question is, how large is large enough? Well, it ain't 2. That's for sure. it may be 25. And this is how things have changed since I was in a statistics class. When I took statistics, my last statistics class was, I don't know, about 1994. The standard, the rule of thumb, as we called it, was a sample size of 25. If your sample size was 25, then regardless of what the population looked like, your sampling distribution was going to be normally distributed. Now, if you read in your textbook, they recommend, I guess the rule of thumb now has changed. It's a sample size of 30. Not much different than 25, but 30. Okay. So what we're looking for in practice, if we want to take a sample from any population and we want to consider the sampling distribution of the sample means, then we want a sample size of around 30. I don't think you'll see in a multiple choice test n equals 25 or n equals 30 being choices. I think it'll probably be n equals 30 or some number larger than 30. If you can do 50, do 50. It's even better. But by the time you get to 30, the extra time and effort that it takes to take 50 samples doesn't really get you any closer to the true population mean or understanding what the true population mean is. Okay, so I tell you what I'm going to do here. I'm going to stop right here with this graph. I'm going to ask you to go to your textbook, read through this section on central limit theorem. And so what I'm going to ask for you to do today after our discussion, I'm not going to ask you to do any problems with the central limit theorem. I want us to just go back to talk about a distribution that is normally distributed. So flip over to page 454 in your textbook. Problems 50 and 53. Okay, neither of these are central limit theorem problems. These are both populations that are normally distributed. I think it just comes out and tells you in black and white that they're normally distributed. So I'll let you, I think question 50 is pretty straightforward. I think you can read through that one. Question 53, I want to give you some hints on it. So suppose that the overall level of all men aged 20 to 34, so young whippersnappers, follows the normal distribution of mean 188 milligrams per deciliter and a standard deviation of 41 milligrams per deciliter. Choose a simple random sample of 100 men from this population. What's the sampling distribution of X bar? Okay, so for A, that's really a question that's asking you to describe the distribution: shape, center, and spread. Okay, so for A, you're going to describe this, you're going to identify the center and spread and talk about the shape. So no calculations for part A. Part B is find the probability that X bar estimates the mean within plus or minus 3 milligrams per deciliter. In other words, this is the probability that X bar takes a value between 185 and 191 milligrams per deciliter. Okay, so that is a probability problem that involves finding the area between two values, and we've done these problems before with finding the probability of a single value. Okay, so here's my normal distribution of mean 188 and whatever the standard deviation is. So this is my sampling distribution. I want to find the probability of being between two values, okay? So you can do that using table A, or you can do that using the Normalcdf function on your calculator. And this particular problem, I think, is probably the only one that is actually easier to use the Normalcdf function on your calculator, but you can use table A for sure, okay? And then part C, choose a simple random sample of 1,000 men from this population, and now find the probability that it falls within that same guideline. So if you can get B, then part C really is just how much more likely or how much more unlikely is that population, is that sample going to fall when n goes from 100 to 1,000. Okay, so that's really all that's about. So I'm going to turn you loose on that one. I think there's enough info in the examples that are in your textbook. You should be able to get through that one. I'll post a few of these notes here online in a little bit, and I'll post the video. You can watch it again. Like always, if you've got questions, feel free to holler, send me a message on Classroom or whatever. Okay? Any questions before we sign off here?
I have a question over the 35 and 38 that you assigned.
Yeah.
Is it supposed to be 38 or is it supposed to be 37? Because 38 doesn't go with.
Yes, it's supposed to be 38 because 38 goes with the example we did in class. The 36 and 38 go together. We did 36 together in class here. And so I really wanted you to follow up with 38.
All right.
I recognize 37 kind of links up with 35, but if you look at the questions, they're about the same question. And so I just wanted to finish the thought with question 36. So even though 37 doesn't link up with, I'm sorry, 38 doesn't link up with 35, just go ahead and do 38.
Okay. And I have a question about 35, part D.
35, part D, okay. Find the probability of attaining a sample of 1,012 adults in which 67% or fewer they drink milk. Do you have any doubts about the result? Okay, so what's your question?
I just don't know how to do it. Like, I can't remember. My mind's going blank.
Okay, so let me give you a couple of hints here. Let me get the book over here where I can get it a little closer. For part D, what you want to know is what's the probability that p hat less than 0.67? Right, so what's the probability that p hat is less than 0.67? So all you'll do there is you'll calculate a z-score like we have always been calculating a z-score. Except you'll use proportion values instead of x values. So your score would be something like 0.67 minus, and the true population proportion is 0.70. If you go back up to the case there, the true population proportion is 0.70. So when you calculate that z-score, it's 0.67 minus 0.70, and it's divided by the standard deviation of the sampling distribution. So you have to recalculate that. The square root of p times 1 minus p divided by n. Once you find the z-score, you just look that up in table A.
All right.
Okay?
All right.
If that still doesn't sink in after a little bit, then just message me on Classroom and we'll go through it again.
Okay.
All right. Well, gang, that's all I got for now. We'll get back together tomorrow.
All right.
See you tomorrow.
See ya.